Good morning, all. My name is Raikhan, and I am a postdoctoral researcher at Purdue University. Today, I will present the part of the study, which is part of the project funded by FHWA program and collaborated together with Clarkson and Penn State University. So, and also I would like to acknowledge the contributions of my co-authors, Professor Janolek from Purdue University and grad student Alberto Castillo. So today I will talk about some of the results on our study on interaction of the natural, non-traditional and natural Pozzolanic materials replaced cementitious systems with different types of chlorides. So before I will introduce some of the characteristics of those raw NNPs, and then follow up with experimental setup and analytical results, and then I will wrap up with some summary points. So before I will jump into my experimental part and results, I'd like to introduce some brief information about the composition and then the reactivity of the materials that we are using. So overall, we are using 11 materials, which are categorized in 4 types. The calcined clay, CCs, NPs are natural Pozzolans, fluidized bed ashes, FBCs, and ground bottom ashes, GBAs. So the amorphous content of the materials, they according to the QXRD data, we got 2 of natural Pozzolans being fully amorphous, and for other materials, the amorphous content is in the range of from 40 to around 80%. As you can see from this plot, this ternary plot that was provided by the group of Professor Rajabipur from Penn State, according to the XRF data, as you can see here, the natural Pozzolans, they are close to the silica edge, which means that they mostly contain they mostly contain the silica, they're rich in silica, and they have some alkalines. And the calcined clays, they mostly consist of the aluminosilicates, and other ashes, the FBCs and GBAs, they are intermixed in the area belonging to the traditional fly ashes. Also, we tested those 11 materials for the reactivity in terms of the heat of hydration at 7 days in cementitious system and consumption of CH also in cementitious system. So overall, if to compare to the reference samples, which is the OPC sample blended with inert filler, all the materials showed some Pozzolanic reactivity. But here we can also classify as the higher reactive materials as calcined clays, the least reactive as ashes, and the natural Pozzolans in between that range. And this trend also agrees well with the calcium hydroxide consumption data. So you can see that the calcined clays, they consumed the highest amount of available calcium hydroxide. In case of the ashes, the FBCs and GBAs, it was the least amount, and then the natural Pozzolans, they again fall in between of that range. But also here, I'd like to highlight the importance of the curing age, that you can see that for the ashes and also for some of the natural pozzolans, the later curing age is crucial for showing the potential reactivity, at least in terms of the calcium hydroxide consumption. So here also I highlighted one material from each category. Here, for example, you can see CC2, NP3, FBC1, and GBA3. Those are selected as the least reactive for scaling test, the results of which will be linked to the study that I will be presenting here. So I will talk about that later on. So in this study, we aimed, by initiating this experimental program, we aimed to study the chemical interaction of paste samples blended with those 11 NNPs with the various chloride solutions. And we choose for that, we followed the exposure regime, the temperature regime of the ASTM C672, ASTM C672, which is all for the scaling test. And we hold our samples up to 50 temperature cycles. And specifically, the goal of this part of the research, it's still ongoing research, it has some other parts, but in this particular case, we wanted to see how the composition of those NNPs can affect to the chloride binding capacity of that cementitious system. But here, in terms of chloride binding, I'd like to emphasize on the formation of less deleterious, even maybe not deleterious and more stable chloride binding, the chloride bearing phases, for example, as a Friedel salt. So back to our experimental setup, we use 3 types of chloride: sodium chloride, magnesium chloride, calcium chloride with the 3% by weight concentration. And the control, also the NNP blended samples, the replacement level for the NNP blended was 25%. Those paste samples were mixed with the water solvent ratio 0.42. They were all cured at 100 degrees RH in moist room and at ambient temperature. And then after 28 days, they were all taken out from the moist room, and the hydration stoppage was conducted by using the solvent exchange method. Then they were dried, vacuum dried. After that, all those paste samples were pulverized and sieved through the 80 micron sieve, and now they are ready to be exposed to the chloride solutions. Then we made the slurry of that pulverized paste powder with the chloride solutions, and then we kept sealed them in the centrifugal in the centrifuge tubes. After termination of the 25 and 50 scaling cycles, we centrifuged them and filtered the solids, triple washed with deionized water, and then again we removed the water with the solvent exchange method, vacuum dried, and then we used the differential scanning calorimeter and quantitative X-ray diffraction methods for analysis. So, sorry. Here you can see the differential scanning calorimeter curves for two materials. So here I choose as an example of the calcined, one of the calcined clays and one of the fluidized bed ashes. So on the left-hand side of you, if we will talk about first on the left-hand side graph, so you can see that after exposure to the chloride solutions, so the black one is before exposure and others are after exposure to sodium chloride, calcium chloride, magnesium chloride, respectively, solutions. So we can see that in this range, we are seeing the appearance of the new peaks. So it means that there is some new formation is taking place. So when we checked with the reference, the literature, the reference literature, so this area, it belongs to the decomposition of the Friedel salt. So we denoted this area as a Friedel salt range. Here also there is from 100 to 125 also there is a first decomposition range also belongs to the Friedel salt. So first feature was we have the Friedel salt formation, and if we will compare them from sodium chloride up to, for example, to the calcium chloride, in case of sodium chloride, the peak is larger. If we compare those two materials, the calcined clay and that fluidized bed ash, we can see that in case of fluidized bed ash, that hump is less. The area is less evidence than in case of the calcined clays. Also, in both cases, after exposure to sodium chloride, calcium chloride, there is a reduction of the CH peak occurs. In case of FBC, it's here maybe we cannot see it, we cannot resolve it more in detail because it already at the beginning has a higher amount of calcium hydroxide. If we will move into the magnesium chloride exposure, we can see that this peak, it started to squeeze into the higher temperature side. So here, in addition to the Friedel salt formation, here we will have the products of interaction of magnesium chloride with the cementitious system. So that might be due to brucite formation, MSH, or any other, for example, also magnesium oxychloride. And also another thing that I want to point out is the disappearance of the CH peak in both cases upon exposure to the magnesium chloride. So using these DSC curves, the area under the curve of the in the range of the peak belonging to the CH, to the calcium hydroxide, and using the calibration curve for calcium hydroxide, we try to quantify the change of the calcium hydroxide. So you can see that in almost in all cases, there is a reduction of calcium hydroxide is going on. And in case of magnesium chloride, you can see it's a drastic decrease in case of the reference sample, but in all samples, it almost disappeared. Then for Friedel salt, so from this result, we said, okay, so this area will belong to the Friedel salt here, right? But in case of magnesium chloride, it was the overlapping. So that's why we, in order to more precisely quantify the Friedel salt, we use the quantitative X-ray diffraction technique. So as a result, here you can see the amount of that Friedel salt formed after the 50 cycles of exposure to the chlorides. And the highest amount of chloride was formed in case of exposure to the calcium chloride, and then followed by magnesium chloride, and the least one in case of sodium chloride. Also, we tried just to see how that area under the area of the curve in the range of the Friedel salt decomposition in DSC curve, and DSC curve, how it can agree with the Friedel salt amount quantified by QXRD. So here you can see that the correlation is pretty good. Then also we wanted to see 50 seconds. Oh, I'm sorry. So also we wanted to see how that formed Friedel salt amount can be correlated to the amorphous alumina content contributed by those NNPs. So you can see that in case of calcium chloride and sodium chloride, there was a good correlation. We can see that it really it has some significance in predicting of the Friedel salt formation, but in case of magnesium chloride, the correlation was pretty bad. Also, maybe I will jump into this part. Also, I mentioned earlier that some of the four materials from each from those four categories as a least reactive were used for the scaling test. Sorry, maybe I will finish. Yeah. We just wanted to see how it will how it can be linked to that our Friedel salt formation and also the alumina content. So as you can see in this graph, we try to correlate the alumina, total alumina coming from all the cementitious materials versus Friedel salt form. There is a good correlation, but when we change the total alumina to the amorphous alumina, we can see that the ranking as the result of the scaling test, they were get closer to each other. So, for example, those ranked from 4 to 5, they fall into close range.